In this video, we'll explore the thermodynamic principles that govern the vapor compression cycle. We'll also learn how to measure its performance through the coefficient of performance, or COP, an essential metric in HVAC design and system evaluation. In this video, we'll focus on three fundamental tools that help us analyze and evaluate the vapor compression refrigeration cycle. First, we'll interpret the thermodynamic processes happening within each component of the cycle: evaporation, compression, condensation, and expansion, by using the TS diagrams. These temperature entropy charts give us insight into how energy and entropy change at each stage, helping us understand where heat is absorbed, where work is done, and where energy is rejected. Next, we'll use the pH diagram, or pressure enthalpy chart. This representation is widely used by HVAC engineers because it allows quick and direct estimation of heat and work input. We'll see how the enthalpy difference across each component relate to system behavior and performance. Finally, we'll introduce the coefficient of performance, or COP, which tell us how efficiently the system operates. You'll learn how to calculate it from enthalpy values and understand typical COP ranges for residential, commercial, and heat pump applications. This will help you evaluate and compare system performance in real HVAC process. By the end of this video, you will be able to explain the thermodynamic processes in the vapor compression cycle using TS and pH diagrams, and calculate the coefficient of performance, COP, for an ideal vapor compression refrigeration cycle from given data. Let's start with a question. Imagine it's a hot day and you walk into a warm room. You go straight to the thermostat and lower the temperature setting. What do you think actually happens inside the air conditioning when you do that? Take a moment to think about it. What is happening actually in the system? In this video, we'll begin to uncover the thermodynamic processes that drive that response. This TH diagram shows the four key processes that make up the vapor compression cycle. From point 1 to point 2, the refrigerant is compressed adiabatically in the compressor. Ideally, this process is isentropic, meaning that no entropy is generated, but in practice, some inefficiency leads to entropy increase. From 2 to 3, the refrigerant passes through the condenser, where it releases heat to the surroundings and condensates from vapor to liquid at nearly constant pressure. From 3 to 4, it flows through the expansion device, where the pressure drops sharply through a throttling process, which is enthalpic. Enthalpy, that means that enthalpy remains constant, but no entropy increases. From 4 to 1, the refrigerant absorbs heat in the evaporator, evaporating at low pressure and temperature. The area enclosed in the PS diagram helps us understand the energy transfers and phase changes involved in the cycles. Now let's look at the same cycle on the pH diagram: pressure versus enthalpy. This diagram is especially useful in refrigeration system design because it allows us for direct visualization of energy quantities. The horizontal axis represents enthalpy and the vertical axis represents pressure. The dome-shaped curve encloses the two-phase region. The enthalpy difference between the outlet and the inlet of the compressor, between state 1 and 2, represents the work input to the compressor. This is crucial in sizing the compressor and estimating its energy consumption. Similarly, the enthalpy change from state 4 to state 1 across the evaporator indicates the heat absorbed from the cooled space. This is useful cooling effect of the cycle. The pitch diagram makes it easier to identify inefficiencies and performance enhancing opportunities in real systems. To evaluate system efficiency, we use the coefficient of performance, or COP. For a cooling cycle, COP is defined as the ratio to the heat absorbed in the evaporator to the work input to the compressor. Mathematically, this is expressed as COP equal H1 minus H4 divided by the difference between H2 and H1, where the H values refer to specific enthalpies at key points in the cycle. The higher the COP, the more efficient the cycle. For example, a typical residential air conditioner might have a COP around 3 to 4, while a high-performance commercial chiller can reach COP values of 5 or more. Heat pumps used for space heating can sometimes achieve even higher COPs under favorable conditions, particularly when the temperature lift is small. These values help engineers and designers choose the most suitable equipment to different HVAC applications. Let's recap what we have covered in this video. The vapor compression cycle consists of 4 thermodynamic processes: evaporation, compression, condensation, and expansion. Each of these involves changes in pressure, temperature, and phase of the refrigerant, which are essential for enabling heat transfer from the indoor space to the environment. These thermodynamic transformations can clearly represent on diagrams that are widely used in HVAC analysis. The DS diagram illustrates how temperature and entropy evolve during the cycle, while the pH diagram allows us to quantify enthalpy changes and energy inputs and outputs. These tools are critical for understanding the real-world performance of refrigeration systems. Finally, the coefficient of performance, or COP, gives us a practical metric for evaluating how efficiently a system delivers cooling for each unit of energy consumed, whether we are looking at a home air conditioner or a commercial chiller. Knowing how to calculate and interpret COP helps us make smarter choices in HVAC systems design and operation. Now that you've seen how the vapor compression cycle works and how we evaluate its performance, it's time to explore the details that make each system unique. In the next video, we'll take a close look at refrigerants, the fluids that circulate through the cycle. We'll compare their thermodynamic properties, safety classifications, and environmental impacts, including global warming potential and ozone depletion potential. Then we'll study real system behavior, identifying how real-world deviations affect performance and what improvement can be made through subcooling, superheating, and optimized component design. Finally, we'll connect everything to actual HVAC practice by examining system applications and configurations, from split systems and rooftop units to chillers and heat pumps. Understanding how the vapor compression cycle is implemented in these systems will help you interpret real installations and make more informed choices. Thank you. Welcome back.